All right, so let's get started. So this is the beginning of our course now, and I suppose that I should start it with some motivation. So motivation, and this is, generally speaking, motivation for what we learn in calculus. And there's two main concepts. The first of which is called the tangent line problem. So imagine like you're looking at a curve. So y, and imagine you have some curve. It looks like this. Okay. And this is some function of x. Okay. Now, suppose, okay, so we know that if we have 2 points, well, let me start by saying this. Let's say, let's call this point there P. Okay. In our goal, or one of the goals of calculus, is to find the slope of the line that touches the graph of that function at that point, and only at that point. So we want, so that's the goal. Like, goal is to find the slope of the line tangent to the point P on the graph of f of x. That thing right there. That's our goal. So how can we do this? Well, one possible way, let me make this graph a little bit steeper just so it'll be easier to see. So suppose it looks like that. And one way that we can do this is we can say, okay, let's say that this point is given by x1, comma, y1. And so that point P is x1, comma, x2. Okay. Now we can consider another point maybe up here. x2, comma, y2. And if we remember from previous math courses, we can find a line that passes through those 2 points, right? So the slope of this line here, I'll use green, there, the slope of that line is given by so y2 minus y1 over x2 minus x1. And if you remember this formula, so I'll call this slope m1. So notice that the line given here between these 2 points is almost like an approximation to the slope of the line here, right? So that slope is kind of an approximation to the slope of the desired line here that passes only through that 1 point. Do you agree? It's like kind of there. Can we make another line that is closer in slope to this line that we want? Well, what about, instead of looking at that point up there, what about if we choose a point closer to this point, maybe here? And if we look at the slope between these 2 points here, then it would look something like, so that's the line passing through those 2 points. And notice now that our new line here has slope that's closer to the slope of the tangent line right there. By the way, these are called secant lines when you're passing through 2 points. When a line passes through 1 point, like this, is called a tangent line. So secant line, tangent line. So another way of writing this, by the way, another way of writing this slope, we could say f of x2 minus f of x1 all over x2 minus x1, right? That's another way of writing the slope, right? Because that's just your y value, that's your y value, right? So how did we, so originally right here, right, this was like our original x2, right? So to get a better approximation, a better line whose slope was a better approximation to the slope of the desired line, what did we do? This is how far we were away from x1, and then we went in, we got closer, right? So we picked a point close, and if we do this again, right, so now instead of using, so this is f of x1 and there. So now, instead of using new values for x, we can do this. We can say x1 plus some value. I don't know. Say, well, I won't get there yet. I'm just going to move really, really close to it. So now I'm going to get a point right there. It's right there on the function, on the graph of the function, and then it's starting to approach the desired one. Okay. So what we can do is we can say, we can start at x1 and we can say, add some value h. So let h be some value greater than 0. And then this becomes, so the slope of the line that we're finding becomes f of x1 plus h minus f of x1 all over x1 plus h. That's like the new value that we pick, right? Minus x1. And then we see here x1 minus x1, so this reduces to that. And for those of you that remember from pre-calculus, this is what's called the difference quotient. Okay. So remember where we started, right? The value, the first x2 that we picked, it was x1 plus some value that moved us over there, and then we had this line that kind of approximated the tangent line. And then we reduced the value of h and we moved over less. and we got a better approximation, and a better approximation. So the idea here is that so as h goes to 0, this thing here gets close to the slope of the tangent line. That's the idea. So we added that much, we went there, we hit that point, found the slope. We added a little bit less, we found that point there, found the slope there. We add a little tiny bit right there, we get that slope. This value, as h gets smaller and smaller and smaller and smaller, is going to get closer and closer and closer to the slope of the line tangent to that point P. Okay. So this is not a static process. So in a course like college algebra or pre-cal, that would be considered like static mathematics. Whereas this idea requires change. H is changing. It's getting smaller and smaller and smaller, and we want to just keep on letting it get smaller and smaller and smaller, right? So one way to think about what calculus is that calculus, the mathematics of change. This problem here is going to motivate the notion of a limiting process, a limit, where we take a value and we look at where it's going, not where it's at, but where the value goes. As something changes, as a variable changes in value, where does this other thing that's related, where does that go? Okay, so this is the first motivating factor of calculus. The second we won't get to for a while. We're going to focus on this first. That we want to be able to see where this goes as that goes there. As the gap gets smaller and smaller and smaller and smaller, that slope converges, or we hope that it gets close or converges to the slope of the line tangent at that point. That's the goal, okay? So in order to do this, we need to understand what that means. As that value heads towards 0, what does that mean for it to go there, right? This is like an infinite process. You can't plug in 0, by the way. Notice that. You can't divide by 0. So we don't know what this equals when that's 0. But as it gets as close as we want to 0, where does this go? That's the idea, okay? So now that we have that motivation, let's look at an example, okay? And this example is not related to the tangent line problem immediately. What we're going to first have to do is understand limits. After we understand limits, then we can come back and we can know what that means. Okay? Okay. So with that being said, this is section 1.2, limits. Okay, so consider the function f of x equals to x cubed minus 1 all over x minus 1. Okay, now the graph of this function roughly looks like, so roughly looks, I think, something like that. Now notice this like 1, 2, -1, -2, -3. Notice f of 1 is not defined. Now, thinking back to what I just erased a moment ago, when that difference quotient, the value h, when h was 0, it wasn't defined, right? We wanted to know where that thing went as h went to 0. This is somewhat similar. F of 1 is not defined. If you plug in a 1, you divide by 0. That's not defined. But we want to know how this behaves as x goes to 1. Okay. So one way to do that numerically is to look at a table. So let's say x, f of x. So let's pick values starting over here, and let's start walking towards 1 and see what f of x is doing. So we can start at 0.75, and then maybe 0.9, then maybe 0.99, and then 0.999. So we're starting over here, and we're walking towards 1, and we want to see where f is going. But then we also want to do that from the other side. We want to start a little bit bigger than 1 and start walking this way and see where f is going when we do that. So again, so maybe a little bit bigger than 1, so 1.25, and then maybe 1.1, and then maybe 1.01, and then maybe 1.001. By the way, I'm really excited. I'm getting another chalkboard in today. So next time, I won't have to erase so much. I'm going to have it much wider. So I apologize today that I keep on erasing and erasing. Next time, it'll be better. Okay, so I'm going to give you a moment to write down those tables, and then I'm going to share my screen with you. Okay. So this is a moment where maybe, so let's use Python. Of course, we could use just a regular calculator to do this, but I want to introduce all of you to Python as soon as possible. So let's use Python to look at these values. You have it all? Okay. All right. So let me share my screen. Okay. By the way, just as proof, see, I'm waiting on it right now. All right, so I'm going to go ahead and open up Anaconda. So I clicked on the little Anaconda icon. It should open up something that looks like this. Okay, and then for many tasks that I do on my own, I just use Spider as my IDE of choice. So I'm going to launch Spider. And again, this is like complete overkill to use Python to do this, but I just want to start getting you in the hang of you know, using Python. So so it'll open up something like this. Okay. You can change the theme of the IDE that you're using by just going to Preferences, and then Appearance, and then you can choose any number of themes. I prefer dark themes, so this is Spider Dark, and that's why it looks the way it does. Yours probably looks white. And then what I would do for all of you, I would suggest doing this. I'd go to Projects, open a new project, find a place where you can put this project. I'm going to put my project in my Spring 2021 folder. And then I'm going to call this Math 2421 Programming. So that's just the name of the folder. And I'm going to create it. Okay. So as you can see, let me put this away. As you can see, let me make sure that there. Okay. So you can see my directory. I'm in this folder. It made a new folder on my in my computer. There it is. And then I'm going to go ahead and I'm going to right click this, or let me say new. New file. And then I'm going to save this file as, notice that I'm in that folder. So I'm going to save it as practice.py. Okay. So notice that my little Python script is inside my folder, or my Spider project. Okay, so when using Spider, you have a console, which acts like a calculator, sort of. You can type clear to clear it out. And then you have a script, and this is where you do like your main programming. I'm going to make a separate video discussing how to interact with Python later. But for now, I just want to do some programming to continue our conversation about limits and where this function f goes as x approaches 1. So I'm going to define a function. I type in def, and I'm going to say f of x, colon, and now I'm inside the function, and I'm going to say return. So what was our function? It was x cubed. So double star is raising to the power. So x cubed minus 1, all divided by, what was it, x minus 1. Press enter, and now I'm out of my function because the white space is no longer there. Okay. So then what I can do is I can say, if you look at the first table, I'm going to call this x left. X left. And these values that we had were, what were they? They were 0.75, 0.9, 0.99, and then finally 0.999. And then the other table to the right of 1, we had x, I'll call it x right. These are underscores, by the way. X right equals, so 1.25, comma, 1.1, comma, 1.01, comma, and then finally 1.001. Okay. So this is our function. These are the, the values that we were curious about. So now I'm going to go ahead and show you how to make a nice little output that shows you the values of f. So I'm going to say print. So as x goes to 1 from the left, okay, and then I'm going to say, so I'm going to print out all the values that I'm going to evaluate f at each of these. I'm going to print it out. So again, you probably don't know any Python. That's fine. You will pick it up as time goes on. So I'm going to say for x in x left, print. Now there's a better way to do this, but I'm not going to show you because it might be confusing. I'm just going to say print x. So string x equals to comma x, comma, space f of x equals to, and then comma f of x. Okay. So all this is saying is, so just so you understand what's happening here, for x in x left, so for this in this, well, what is that? It's this right here. So what this for loop is going to do is it's going to take x to be this. So then that will appear there, and then it's going to evaluate the function we defined up here at that x. And then it's going to loop around and then look at this here, do the same thing. Then it's going to look at this here, do the same thing, look at this here, do the same thing. Okay. Okay. And again, you will pick this up with time. Okay. So now I'm just going to take this and copy it and paste it. So now I'm going to look at as x goes to 1 from the right. And I'm just going to change this to be x right. And just because I want it to look nice and pretty, I'm going to put like a white print statement here. All right, so take a moment to look at that. And you'll, once I press play here and run this, you'll see kind of what this is doing. So I'll give you a moment to catch up. Okay. So let's see what the output of this is. So this was just a print statement that printed out that. And then for x in there, so notice 0.75. 0.75 is right there. And then f evaluated at 0.75 is this. And then it moves over to 0.9. And then evaluates f at 0.9. And then it moves over here to 0.99. And then evaluates f at 0.99. And then same thing. So that's what this for loop does. For x in there, it just picks that one, then that one, then that one, and that one. And you do whatever you want with it after your x has been picked. And then here, for x in this one now, so it picks x to be that, 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 and that, that, and that, and then it evaluates this function at each of those. Okay. So it's just a nice little output, right? So, okay. But what's happening here? Where is, so I'm going to go ahead and fill in my table now. So we have 2.3-ish, 2.7, 2.97, 2.99. And then when we go from the right, we have 3.8, 3.3, 3.03, 3.003. Okay. So let's look at the screen behind, or my blackboard now. So notice that as we approach from 1 from this side, which is up here, right? Where is the function going?
When you approach from where?
Actually, this should be like that. 1, 2. It's heading that way, right? As we're going this way, the y values are heading up, right? So this is 1, 2. Okay. Actually, it's like that. That's 1, that's 2, that's 3. So as we're going this way, we're going up. Now, if we look at the right-hand side, is we're going that way. 3.8, 3.33, 3.03. We're going down, right? So where do you think this function is going as x gets closer to 1?
It's approaching 3.
I can't hear any of you.
Sorry,
It is like right in front of you, right here. So it looks like that's going to 3 as x goes to 1. That's what it looks like. Do y'all agree? So this is the idea that we want to try to capture, right? This is let me write down informally what this means. But everyone agrees, like if you look at the table, we're getting closer to 3 there, and we're getting closer to 3 there. Okay. So informally, if f of x becomes arbitrarily close to a single number L as x approaches C from either side so either side of C, then the limit as x approaches C of f of x equals L. So this is the informal definition. So definitely informal. But also, this is important, a single number. If you're approaching two different numbers, then it's not going to be the case if that's the limit. Okay. So let's look at another example. So let maybe f of x equal to 1 if x is not equal to 2, and 0 if x is equal to 2. Okay. Now, what does the graph of this look like? So if you pick any x that's not equal to 2, then the value of f is going to be 1, right? So the graph of this thing looks like this. Oh, there's x equals to 2, so there's a hole right there. And it's 1 everywhere else, but then it's equal to 0 when x is equal to 2. Do y'all agree that that's the graph of the function? This is, by the way, a piecewise defined function, if you remember that word, piecewise. Okay, so notice now in this case, f is defined at x equals to 2, right? So f of 2 is equal to 0. It's defined. But what about the behavior of the function as x approaches 2? Right? In fact, like we can get so this idea of arbitrarily close is going to pop up a lot in calculus. So suppose that we're coming from the left-hand side and we're heading towards 2, right? So we evaluate the function there, it's right there. Evaluate the function there, it's also right there. The y value of the function, it's 1, right? So if I like f at 1, the value of the function is 1. f at 3/2, it's also 1. As we head this way, the function is always approaching, it's always at 1, right? And then here, as we head this way, what's the value of the function approaching? It's always at 1, right? So even though the function is defined at 2, that's not how it behaves as x approaches 2. So regardless of whether or not it's defined in there, we have that of that f. Okay. Okay. Just that, I guess this is, it's important to note that like that doesn't matter. Right? What matters is the behavior of f as x is changing. Again, like you have to think back to a dynamic process of changing values of x. Okay. All right, so let's look at another example. Let's say so what does the graph of this look like? Well, all of you should know roughly like what 1 over x looks like. So 1 over x is like that. But 1 over x squared is going to be something like that. Okay. So what can we say about that? Okay. So let's just like look at the graph and kind of see what's going on. So as we head to 0 from the left, so we pick like x right there, that's the value. We pick x right there, that's the value. We pick x right there, that's the value. It's going up, right? And it's always getting bigger and bigger and bigger. If you approach 0 from the right-hand side, the same thing happens. Pick x right there, there. It's always getting bigger. It's going up. Okay, so we would say that this is not a single number. So it does not exist. And this is a case where a limit doesn't exist because, so this is unbounded. We can get, as x gets close to 0, this becomes arbitrarily large. There's no bound on it. Okay, let's look at another example. Let's look at f of x equals to the absolute value of x over x. Okay, so the absolute value is just the positive value of the number that you put in. That's one way of thinking about it. And so if x is positive, then this is just x over x, which is equal to 1, right? And if x cannot be 0, it's undefined at 0, so there's a little hole right there, and then so if x is positive, that's what the graph looks like. Now, if x is negative, it's like x over negative x. So it's going to be -1. So that's the graph of f of x. Okay, so I'm like curious to know the behavior of this as x approaches 0. So what's going on here? Okay, so all right, let's start from the left. As we approach 0 from the left, where is this going to? And you can use your mics, by the way. So what's the value of f when you pick that x right there?
-1.
It's going to be -1, right? What's the value of the function when you pick x right there? -1. What's the value of the function when you pick that x right there?
Still -1.
-1. So from the left, it looks like this heads to -1. Right? Like if you didn't know anything about what was going on over here and you were just coming this way and you were like evaluating the function, just walking along, checking what the function was, you would think that it was going to -1, right? Okay, so suppose someone else is over here and they're walking towards x equals to 0 from this side. So if I pick x right there, what's the value of the function? 1. If I walk a little bit further and I pick another x and I look at the value of the function, 1. If I walk a little bit further, pick a value, look at the function, 1. So from the right, where does that look like it's going to? +1, right? So again, this is a case where this limit is not going to exist. And if you look at the informal definition of the limit, look, it has to approach a single number from either side. As we're approaching 0 from the left, it goes to -1. If we approach 0 from the right, it looks like it's going to +1. These are two different numbers, so the limit doesn't exist. Does that kind of make sense a little bit? Okay. All right, so let's look at another one. The sine of 1 over x. So just recall the sine function oscillates back and forth, right? This function happens to look like this. Like that. And then like that. That's what it looks like. Okay. So if you probably forget, because most people forget trig stuff all the time, but sine of pi half is equal to 1, and sine of 3 pi over 2 is equal to -1. And if you keep on like adding, yeah, so if you take that and you add pi, you get that. If you add pi to that, so what is that? So 3 pi over 2 plus pi, it's going to be equal to 5 pi over 2. So then sine of 5 pi over 2 is going to be equal to 1. There's like special values where sine is equal to 1. That's and sine is equal to -1. So if you start there, it's equal to 1. You add pi, it's going to be equal to -1. You add pi, it's going to be equal to 1. You add pi again, it's going to be equal to -1, so forth and so on. Okay? So what we can do is say, let's look at so if I plug in 2 over pi into x, so like, I'm just being careful for those that might be rusty on algebra right now, but like sine of 1 divided by 2 pi is equal to sine of pi over 2. You take the reciprocal. When you divide by a fraction, you evaluate it to the reciprocal. So if I plug in that, it's like evaluating sine at pi over 2. And we know what that is, it's equal to 1. Okay. So then let's look at 2 over 3 pi. Notice that this is smaller than that, right? This is smaller than that. That's going to be equal to -1 because it's like evaluating sine at the reciprocal, sine of 3 pi over 2. Okay. So let's look at a smaller one. 2 over 5 pi. Well, that's like evaluating sine of 5 pi over 2 because you plug it in there, take the reciprocal, it's equal to 1. And you can keep on going with this trick. So the next one, if you add pi, be 7 pi, which is -1. And that's smaller than that, that's smaller than that. We're getting smaller and smaller and smaller. So basically what's happening as we approach 0 from this side, right? We pick a value and then it's at 1, right there. And then we go a little bit closer, then it's at -1. We go a little bit closer, it's at 1. We get a little bit closer, it's at -1. It's oscillating between 1 and -1. So this is another case where, so as x is going to 0, sine of 1 over x, that then does not exist because it oscillates between these two values forever. Okay. We'll give you a moment to work it out, but write that out. All right. Okay, so now we should probably talk about the formal definition of the limit, not the informal. But before doing so, because it is rather involved, let's go ahead and take like a 10-minute break, and then we'll pick back up at 1:10. Okay. So I'm going to pause the recording now. Okay, so now that we're back, we're going to talk about the formal definition of the limit. I will say that this is probably the one definition that students that have made it through Cal 1, Cal 2, Cal 3, through all of the calculus courses, the one definition they probably don't understand. It's a pretty intuitive concept, right? Where does the function go as you approach some number, as x approaches some number? Like, where does it go? But the definition is precise and technical to encapsulate this idea. Now, I'm going to describe it in terms of, not in terms, but I'm going to describe it with a topological picture. Personally, I didn't understand this definition until I took a course called topology and realized that the definition was a lot simpler than what it looks like in the textbook. So I'm going to start with a very vague looking picture. It might not make sense at first, but then at the very end, I'm going to translate it back to the definition that you see in your book. So, okay, well, the way that we deal with functions, the way that we graph functions, right? We have some function f, right? And we pick a value here, and then we get another value up here, right? That's how functions work. But this is just like a collection of real numbers, that line. So we pick something from that set of real numbers, that collection, and then f takes that number and it puts it somewhere in here. But that's just another collection of real numbers. So really what we can think of as functions as in a more general picture with the following. So imagine that inside of here are all real numbers. Okay. And f takes these things and it spits out another real number. So you pick something here, then f puts it over there. It's the same idea as plotting in the Cartesian plane. You pick something here, and then f plots out something over there, right? Okay, so here's the definition I'm going to introduce, okay? So we're going to say that the limit as x approaches c of f of x equals L, okay, when if for every number epsilon greater than 0, so for any number epsilon greater than 0, there exists another number called delta greater than 0, so that if the distance from x to c is less than delta. That's just the distance. How far away is x from c? If it's less than delta, then the distance from f of x to L is less than epsilon. Distance, right? Like we all know the concept of this distance. How far are you from something, right? Okay. So we're going to suppose now that this is the case. So we're going to suppose the limit of f of x as x approaches c. We're going to suppose that that's equal to L. Now, if that's the case, then it must satisfy this definition. Okay? So, all right. Notice that, so where is C? C is something in the domain of F. So I'm going to say maybe C is right here. Okay? And then L is something that F approaches, right? So F is somewhere over here, right? So maybe L is like right here. And we are assuming this. Okay, we're assuming that the limit as x goes to c, f of x goes to L, which means that this has to be true. Now here, this is just any positive number, epsilon, any positive number. And we're going to eventually be concerned with the distance between f and L being smaller than that number, okay? So one way that we can like imagine this, like imagine like you put your arms out like this, and you have some distance to your arm, right? And you make like a circle around you. Anything that's within your arm's length to you is within that distance to you, right? So what I'm going to say is I'm going to like put out an arm of length epsilon. And then I'm just going to twirl around. So you agree, like if you're inside of there, then you're within distance epsilon to L, right? Okay, so we just pick epsilon arbitrarily. So just pick some positive number epsilon and make a little ball. So anything that's in that ball is within distance epsilon to L. Okay. Okay, so we picked our epsilon. So then there must exist another number delta, so that if the distance from x to c is, distance again. So now delta is looking at the distance from x to c. So maybe I'll use pink. I'm gonna do the same thing over here. It's kind of hard to draw a little delta, but let's see. Yeah, delta. Okay, so that's my delta. And then I'm gonna do the same little ball thing again. So, okay. So after we pick epsilon, if this is true, we get a delta. Okay. All right, so we're assuming that this is true. Okay, now, so if the distance from x to c is less than delta, then the distance from f at that x to L is less than epsilon. So what does that mean? It means that, okay, let's pick something in there. call it x. It satisfies this. The distance from x to c is less than delta, right? It's in that little ball. Which means that this must happen. The distance from f at that must be less than epsilon. So where does f take this? This would be f at that x. It better be inside that ball. Because any x that lives in there must be sent in here. Right? In fact, any, like I could just pick another one. Maybe like call it A. Where does A get sent? Well, it's in there. It better be sent in here. So it's like F at A. Does that kind of make sense? Like if it's in this little ball, it better be in that little ball. Provided this is the case. Now what's special about this is that we picked any epsilon, any positive number epsilon. So let's look at this again. Okay, so here's L, and maybe here's C. Let's pick a different epsilon. We can do that. The last one we picked, what, it was like that long? Like that length was the length of epsilon. So maybe we'll do like a little tiny epsilon, smaller. Well, if this is true, even though that's a tiny little epsilon that we picked, there must be a delta that corresponds with it. So maybe no matter how small of a little ball we made, if this is true, right, then this has to be satisfied, so there must be a delta. Then the same thing holds. Any x that you pick inside that little ball, where does it have to go? F has to take it inside of that little ball. And by the way, this is like all the real numbers are crammed in here. Right? So inside this little ball, there's an infinite number of real numbers. We can assume that. So that means that infinitely many of these points, every single one of them, infinitely many of them, get sent in to that ball. So infinitely many of the things here get sent as close as we want to L. We could take an even smaller delta, smaller epsilon, or even a smaller epsilon. It doesn't matter how small we pick it, as long as it's positive, right? You can pick, like epsilon could be like, I don't know, like 1 over 2 to the power, like 10,000. That is an incredibly small number, but it doesn't matter. There's still going to be some distance around L, some tiny little distance, and there's going to be a delta where we can make a little ball around C in infinitely many points, because there's going to be infinitely many points in that ball. All of those are going to be sent to within that distance to the number L. This is the idea behind limits. No matter if this is true, right? Then no matter how small a step you take away from L, there's infinitely many numbers that are sent by the function to be in there. Okay, so this is more or less like you would see something like this in like a topology course. But I think it's easier to understand distances when I draw balls like this. And it's not so detailed. Now let's go back and let's look at the Cartesian plane and see what this means. All right, so here's the definition or a modification of the definition you'll see in your textbook. So the limit as x approaches to the f of x equals L if for all epsilon greater than 0, there exists delta greater than 0, so that the absolute value of x minus c less than delta implies the absolute value of f of x minus L is less than epsilon. By the way, absolute value taken of the difference of two numbers, what is that between them? Like, for example, two and six. 1, 2, 3, 4. The absolute value is the distance between two numbers. The absolute value of A minus B is the distance from A to B. So this looks exactly like what we just looked at, right? If I just wrote distance here and distance there, that'd be the same thing. So let's look at like an example. What does that graph look like? It looks so this is that first function we looked at. X cubed minus 1 over x minus 1. We already know what the limit is. We know the limit should be 3, right? Okay. So we claim that the limit as x approaches 1 of x cubed minus 1 over x minus 1, we claim that's equal to 3. That's what we said at like the beginning of our lecture, right? So here, that's our limit. And what's our value for c? That's our c right there. So pick any epsilon you want. Maybe, I don't know, let's take epsilon equal to 1/2. So here we are. So let's make a little ball. Right? So go up 1/2, and you circle around. So this is like L plus epsilon, and that's like L minus epsilon. That's like the radius of the ball that we drew, right? Like, you can even like picture it. So anything in here is within epsilon distance to L, right? So as before, this implies that we get a delta. I don't know what that delta is, but visually I can probably pick one. So maybe like, so this is, C is equal to 1, by the way. So it's a half. So maybe like to be safe, maybe I'll just like kind of go like a quarter, like a quarter left and right. I don't know if this is like a good value. I'm just like pictorially, it looks like it's gonna work. So maybe delta's a quarter. So then let's go left and right with distance. So like, and again, you can kind of see like the little ball that would have been there, right? So we have these like open intervals that at the center of those open intervals is L, and they have distance around them. They have epsilon that way, and then delta that way from the C. So what does this definition mean? It means that if I pick something like right there, so I guess like, hopefully this works, like maybe let's pick like X to be 3/4. Right? And let's hope that it goes to where it needs to go. So what is that? So 3/4 cubed. Oh, actually it needs to be fully in there. So let me say 1 minus an eighth. What is that? 7/8. Yeah, so 1 minus an eighth is definitely in there because I went to the left a fourth, right? So that's in there. So let's take X equal to 7/8. So then f at X is going to be 7/8 cubed minus 1 all over 7/8 minus 1. What is that? So it's going to be 7/8 cubed minus 1. So negative 1/8. I wish I had a calculator, honestly. I just hold on. Okay. 7/8 cubed. So that's going to be 0.669-ish minus 1 over negative 1/8. So minus 1. So this is like saying negative 0.33 stuff over like negative 0.125. Okay, so what is that? So roughly 0.33 divided by 0.125. So that turns out to be roughly 2.68. So L was what? L was equal to 3, we claim. And then what did we pick epsilon to be? 1/2? So yeah, that right there is 2.5. that value there gets sent right about there. So that would be f at 7/8. And where did 7/8 come from? It came from there. So the idea is that anything I pick in there will be sent in there. And if I pick a smaller epsilon, I might have to have a smaller delta, but still anything I pick in there will be sent there. Okay. So now I don't know if that's the correct epsilon. I mean, not epsilon. I don't know if that's the correct delta. I just took a guess. I looked at the graph and was like, hopefully if I pick delta to be right there, it worked. But how can we do this in general? And how can we find delta? Not that you'll be asked to find it very often, maybe once, but it's important to know that there is a way of finding it, the correct delta. Okay. Okay, so claim. Let me just pick an easy one. Okay. Limit as x goes to 2 of 3x minus 2 is equal to 4. That's what I claim. So now we're going to actually give a formal proof of this. But in order to do that, I'm going to need some scratch work to figure out what delta needs to be. Okay, so this is like my scratch work over here. So I'm gonna, scratch. So I want 3x minus 2 minus 4 to be less than epsilon. So that's like my function, that's my limit. And that's so like we want this. And again, this is just scratch work, right? So we want to find a delta that makes this true, right? Okay, so what does this simplify to? This is 3x minus 6 less than epsilon. And this simplifies to 3 times x minus 2. Like that. So now we have positive number times this, so we can just take that out of the absolute value. And we see that that's a 3. So if this holds, then this holds, then that holds, then that holds, then that holds. And this is what we want to hold, right? So we just say, okay, this will be our delta. Remember, the delta is dependent on epsilon, right? So it makes sense that delta is going to be written in terms of epsilon. Okay, so the proof of this would look like, okay, let epsilon be greater than 0 and choose delta equal to epsilon over 3. Okay, so then if that's true, if you pick an x that satisfies that, right? We have that this is the same thing as writing this. Which is the same thing as writing this. which is the same thing as writing and which is the same thing as writing so if that holds, then that holds, and we're done. So this definition that we're using, that's called the epsilon delta definition. And this right here, this is an epsilon delta proof. The one topic that probably all of you will forget and most students do forget is proving things with this definition. Yeah. So as data scientists, you don't need to worry about this, but it's important to at least know about it. Okay. The formal definition of a limit is really about distance. Right? The distance from f to the limit is less than epsilon, then you can always find something in the domain that gets sent to something within that distance. And to find your delta, if you're given an epsilon, you just have to work backwards. Like assume that and then try to deduce what delta has to be. Okay, so that will be it for today's lecture. I know it's kind of, the epsilon delta stuff is a little annoying, I know, but it's important that you at least know it. Okay, so I guess y'all stay safe and healthy, and I will see you next week.
See you
Yeah,
next
good day,
week.
Professor. Thank
And
you.
I'll post suggested homework problems over the weekend.
Yeah.
So,
Perfect. Thank you.
all right, see y'all then.
Thanks, sir.
Thank you.
Thanks.